Hello, good afternoon, everyone. My name is Taranjit Singh, and along with Frederick De Brode, uh, we are going to talk about the title Improving Identification and Control Effort for Systems with Varying Topology. That's the title for this webinar. Before we move forward to, to the next part and discuss about the whole topic, there's a bit of an announcement. The cameras and microphones of all the participants are muted by default. Um, you can post the questions during the presentation in the chat box, but they'll be answered in the Q&A session at the end. Also, we'll be recording this event and share it at the later moment. Right. I'm just going to start with introduction, or basically I'll talk about the systems with variable topology. So when we say system, we actually talk about collection of subsystems or the subcomponents. And of course, good control, what we mean by good control, that they should operate in a good way. And we'll talk about this topology in general in the later stage. But the main difficulty in control design for such a system that consists of subsystems is when the connection of subsystems can vary over time. And the main question that arises, how can we maintain the system performance even though there are some changes in the connections of these subsystems, or rather how to control such a system. So in a nutshell, where does this fit in Flanders make? We often work in dedicated modeling and identification for control. And some of the challenges that industry pose is to how to control systems with variable topologies. So you might have heard this word topology in different engineering aspects, like bus topology is quite common, tree topology and mesh topology and so on. But I'll go more in detail. What do we mean when we say systems with variable topology? And in finalizing this whole thing, we want to actually show how do we tackle this challenge of controlling the system with variable topologies. So, like I said, system can consist of different subsystems, and they can actually form a network in such a way. There are subsystems, like for example, you can see it in this figure. There are some subsystems. They can communicate with each other, and there are many subsystems. And like I said, a good operation would be actually if it has a good control. When these topology or the connection between these subsystems change. A good example is, let's say, a microgrid, where you will see that at some point there might be some house connected, some batteries, some EV chargers connected. And what you want to do is actually balance the load. And in such a way, you actually balance the state of power and state of charge. It might happen that most of the time these things might not be connected. So what I mean is the topology actually changes, and you would still be able to meet the supply and demand by balancing this state of power and state of charge. Another good example is a central HVAC unit in a building. Let's say you have different rooms like living room and bedroom. It might happen that you want to heat one living room or all of them. And suppose if you have a door connected between two rooms, like for example, in this third figure, it might happen that you might have to open and close the door. And in this way, the dynamics or heating of these rooms will change. And the main goal here is actually temperature balancing. Another example is an air net. So basically a pneumatic system. You have compressors, you have filter regulator and lubricator, and then you actually have a pressure uh, and flow, basically controlling the load or actually meeting the demand. And it might happen, like for example, over here, a valve V2 can change direction. And during this changing this direction, you change the topology inside the system. And you can see the difference between these two figures is the direction or the flow of the green line. And the main goal here is actually control the systems, or rather balance the pressure. I'll talk more about these components because this is where we actually validate our examples or validate our algorithms to control systems with variable topologies. Um, so what's the main challenge here? Like I said, an example over here, just a building with central HVAC unit. Now, if these number of rooms, or rather this number of subsystem or component when it increase, there will be increase in number of topology and combinations, because it might be possible to just heat one room or all of this room, and the number of uh, topologies increase exponentially with the number of subsystems. So when you actually want to design a controller for this whole system, you will have increase in number of model identification. And why is that? Because not all combination will have same dynamics. What I mean is heating one room will not be the same as heating all the rooms. And what we actually want to do is to reduce this effort. If you reduce this effort, you actually reduce the control design and development complexity itself. And that's what the main challenge and we'll be trying to tackle here. So usually when we want to start controlling systems with variable topologies, we actually follow a general flow. Uh, the most commonly used or the most classical way of controlling this subsystem is so control systems with variable topologies is to go for state of practice controllers, which are basically model-free controllers. You don't have to model anything, just try uh, ad hoc PID controllers and try you design trial and error or design PID controllers with trial and error. Of course, you do not consider the model. So what you don't have to spend much time in modeling or identifying the system or even subsystems. So this is easier in a way that you don't have to spend much effort. But at the same time, your control performance might not be good. Of course, you can argue that you can spend more time and do more trial and errors, but then this blue dot will actually see fading away exponentially. Uh, One way is to actually consider the modeling part as well and just try to model all combinations. So identify all the combination, identify dynamics of all combinations, and then start controlling design, but considering the worst case scenario. The drawback, you have to actually go through this exponential curve or perform identification procedure exponentially with respect to the number of subsystems. So that would actually increase the complexity of designing and development. But at the same time, you will see an increase in control performance because this controller that you will design will take care or will actually be based on the worst case scenario. A good strategy would be to actually design a scheduling controller. So basically, you actually model all the subsystems or dynamic or combinations, and then you design controller for all combinations. Of course, the effort will increase even more because now you're designing the controllers as well with respect to other subsystems or different topologies. And there you will see the control performance increasing, but at an expense of spending a lot of effort in designing and development of the control system or control design for variable topologies. So the goal is rather simple, like how to get over here where you don't actually have less performance, but you have a better performance, but also you don't have to spend a lot of time in designing and development of the controllers for the system with variable topology. Or if you want to break it down, you actually want to minimize the control design and development complexity and maximize the control performance. And that's how we will show you here how we actually proceeded or how our tools helped us to achieve. And for that, we actually went for state-of-the-art adaptive model predictive control, where what we actually do is we design model predictive controller. The key advantage is you only have to model the subsystems and not all the combinations, but actually you identify the topologies in such a way and make your controller adaptive to these topologies, hence the name adaptive model predictive control. And because of this linear curve that you oversee, that you only have to model subsystems, not all topologies, you will reduce the effort and you will have an increased control performance. But this is what I'll show you um, by the end of this presentation. This is also the key takeaway of this webinar. So we actually spent a bit of an effort in designing, or rather researching on these several topics, comparing certain topics, and we found out that we will actually achieve this green dot over here, increasing control performance, reducing the design and development complexity. Uh, yes, I've been talking about variable topologies quite a lot, but how do we obtain these topologies? Well, you will remember this figure from the previous presentation, previous slides. If you have these subsystems and they are connected with each other, consider these subsystems as vertices and the communication as edges. You can actually map your whole system in a graph theory. And the key result of this graph theory is a Laplacian, which actually encompasses the communication among these subsystems. And this is the base for our method, where you can actually uh, boil down any type of a network into a simple graph, which is known as, or simple matrix, which is known as Laplacian. And this will be used in our method. So how to control this subsystems with variable topologies? Um, of course, we had to make some assumptions. We assume that we know topology. If we don't know topology, we might be able to observe the topology on the fly. This is quite useful by monitoring, let's say in the building, if you monitor which door is closed or open, or in a pneumatic system, you monitor which valves are open or which valves are switched on and off. But if that's not the case, uh, I would point you to look into robust MPC or scenario-based MPC. But this is out of the scope in our uh, research that we did and in our webinar as well. But we'll focus on this part where we actually can observe the topology on the fly or in real time. Topology is rather simple. You model and identify each subsystems, like I said before. So basically, your complexity is not exponential anymore. It's just linear. The number of subsystems, you model and identify those number of subsystems. You define the topology using Laplacian, or rather graph theory. And once you do that, you actually formulate your topology in this form, and you add a virtual leader. If there's a reason for adding this virtual leader, I'll come back to it again. And then you formulate the model predictive control optimization problem with adaptive Laplacian, or rather the adaptive communication between uh, the subsystems, or rather variable topologies. So the goal of model predictive control would be at every time sample to minimize the cost, usually the output that need to be tracked with the desired reference, subject to the model that we actually identified, the communication between subsystems. So Laplacian would be an adaptive parameter which can be observed in real time, input and state constraints. Uh, of course, we have an a pneumatic system in our laboratory, and we actually validated this methodology or this algorithm in our pneumatic system. So just have to go through. I'll just explain you what these components actually means. You have a compressor that's providing the pressure that will be used for supply. We have filter regulator and lubricator. We have flow directional flow valves. We have pressure regulator valves, and we have these discrete valves like V1, V2, V3, V4, where, which can be considered analogous to the doors in a building. So when you switch on and off, you can actually change the directions. So we also have certain tanks. You can actually fill or empty these tanks, and the dynamics actually is different in emptying and filling these tanks. It can be considered as a capacitance in a circuit, and then you have the out pressure that's connected to a load. Now, in this case, we can observe the valves and hence we can observe the communication topologies. And this also fits in the description. Of course, we had to make some assumptions in modeling the pneumatic system, or rather the subsystems, which is we consider ideal gas equation adiabatic process. We'll be neglecting valve dynamics. Of course, we assume that they switch so fast, we don't really touch that. For the communication, we actually consider leader and follower communication with a virtual leader. The reason behind choosing this virtual leader is we assume there's a delay which can occur due to the tubes in this pneumatic system. And the tanks are considered as the followers. So basically, they are the subsystems. Of course, we consider bidirectional communication. What it means is each tank can communicate with the other tank, but also this can be extended to just one-way communication. And the communication has a spanning tree. For the MPC control, we have to assume that all systems are stable and or stabilizable, because that's the cost we pay for introducing the Laplacian or making the algorithm as adaptive MPC control. And we assume that we have a quadratic objective cost. So what this MPC control does is it actually solves an optimization problem every sample time. And this sample time is usually fast, depending on the dynamics of the system. So the goal here is basically you have to track a reference or basically provide, in our case, it's actually providing a output pressure to the load. We also put penalization of input and terminal cost for the stability. Subject to the model of system, you can choose either linear model or non-linear models. The communication among subsystems, like I said, using the graph theory, you can obtain this big L, which is basically a Laplacian, state and input constraints. So what this basically, if you solve this optimization problem every sampling time, you will be providing optimal input that actually provides the output, no matter how the Laplacian changes or no matter how the topology varies. For modeling the subsystem, we chose linear time varying models because, like I said before, we have tanks in there, and emptying the tank is not the same as filling the tank. So the dynamics actually depends on the pressure as well. And this is how we move forward. So I'm just gonna go towards the results. Um, but before going that, what we did basically, we designed an MPC controller, which is adaptive because it considered the observed Laplacian. What it means is it actually considers the variable topology, or it takes into consideration of this changing communication. We deployed this controller on a real-time industrial PC, and we validated it experimentally, this whole system on a pneumatic system. And when I say how fast this optimization is doing, it's working every 10, 20 milliseconds, 10 or 20 milliseconds, depending on the application we chose, and it always solving under 10 milliseconds. What it means is it's updating the control input to provide it to the system, depending on the variable topology, and it's solving every 10 under every 10 milliseconds. So it's fast enough to update to provide this optimal input coming out of this optimization problem. So we had quite a lot of results. We did a lot of sensitivity analysis. We validated and compared it with a lot of controllers that we had, a lot of state of practice controllers. We also have, so I didn't go much in detail, so it's rather high level in theory. So if you want to look into the methodology, we have paper, two publications on this. Not just that, we also presented the real-time demonstration in Flanders Make Symposium in 2022. And this is basically also the results coming, that what you see is the video coming from the symposium. But again, I'm not going to talk about what are the results, but I'm just going to talk about key takeaway. Like I said, we compared our algorithm, which is the adaptive MPC or the methodology that we used to design such controller, with different uh, different classical controllers that I mentioned before. So you have state of practice controller, the robust controller worst case scenario, and the scheduling controller, which is basically controller um, that you can switch between when the topology changes. So let's see how the adaptive MPC compared with a state of practice controller. Since it was tuned ad hoc, it didn't consider the modeling, so it was model-free control design. There was a lot of overshoot when there was the topology change. And you can also actually observe this. If you see the ad hoc aggressive PI controller, you will see there's a bit of an overshoot. The red part is an overshoot, while the green part is the MPC controller. So there was reduction of overshoot nearly 100%. Also, you will see that the control input or the voltage applied to the valve had some oscillations once the topology changed, and this was also reduced in the MPC controller, which is the green curve. With respect to the robust state of practice, what we found out that we utilize 5% less energy when we use adaptive MPC controller. Also, the response was faster with compared to the robust state of practice. As that was the performance, but if you look at the design and development time, we tried to design controllers for different um, combinations, or rather for all topologies, and we just designed this adaptive controller, and the design and development time was reduced from 64 hours to 11 hours. So what is the key takeaway is we didn't even just increase the performance, we actually also reduced the design and development time, and hence we improve the identification and control effort with improved performance. Of course, uh, this is not the perfect solution. We still had some limitations. We actually just put static loads. We didn't have an uncertain load in the demand. We also wanted to know how it will perform if we actually had uncertain load, or if our MPC would have introduced an offset in the control input. Also, we have certain state of the art we didn't compare. We wanted to know how it performed uh, for higher dynamic systems. Of course, the most important part is the scalability of subsystems. We tried up to 3 subsystems, and the solving time was always 10 milliseconds, under 10 milliseconds for MPC. We would like to know how will it compare uh, to the systems when the subsystems increase, and how the solving time will increase, or will it remain the same. That's all from my side. If you have any questions, please don't hesitate to post these questions on the Q&A chat box.
Okay, thank you, Taranjit, for the presentation. There are no questions so far, so I suggest we wait a little bit longer to see if there are more questions coming in. Maybe while we wait, I maybe have one question for you.
Yeah.
We talked about it already a little bit in the presentation, but can you maybe summarize or give a brief overview of which kind of companies with which kind of applications can benefit the most of using this kind of methodology?
So I think I go back to the examples which I showed before. So we have so we validated this methodology in a pneumatic system, but this can be useful in AirNet, where you have different topologies coming into account. For example, we have Atlas Copco with AirNets. So this can be useful in those applications. Then we also have this temperature balancing, where you have different topologies. One of the companies that have this possibility or have this or needs to tackle this problem is Duco, where they have different topologies where you have different combinations that's possible.
Yeah. Okay. And if there are people listening who might be triggered by this idea, how can they get started with this? What do they need or need to do, or do you have any idea for that?
So, so when I said where does this fit in Flanders make, we actually uh, perform, or we actually look into more dedicated modeling and identification for control. So we build the tools that can be useful just not for modeling identification, but also for control. The tools that I mentioned, MPC control, we have the possibility to um, improve the design and development time, and actually have an adaptive control. Like for example, the control where actually you are able to adapt to variable topologies. So we have certain tools. Um, if someone really wants to start looking into, like I said, you can look into some of the. So if someone is interested in the classical controllers, we have certain references over here. This is a recorded session, so this will be there already. And not just that, we actually have, this is an overview of a publication. Uh, so two publications basically. The main one is it was recently published in European Control Conference. So that will actually provide you the starting point, or also a low level overview of the whole scenario that I've shown here.
Okay, great. Thank you. There are no other questions so far, so I suggest we just wrap up the session because we're also at the end of our time slot. So if people have more questions, don't hesitate to still ask them in this Q&A chat box. We will still see them coming and try to reply to you individually afterwards. But for now, we're just closing this session, and I give the last word to Taranjit to wrap up this webinar.
All right. Thank you so much, attendees, for listening to this webinar. Again, as Safe suggested, if you have any question, you can keep on posting on this Q&A chat box, or you can also contact me. And that's it. Thanks a lot.